So with question 32, we're told in the following exercise, solve the following system of equations by substitution. So we are transitioning out of graphing, and now we're looking at the more probably traditional methods, because we're going to also look at elimination, that you will use to solve your systems of equations. Again, to reiterate what I mentioned in some of the graphing videos, if you're told in the directions to use that method on an exam, then of course that's the method by which you must solve the system. But in the real world, if you have the choice, you will want to solve by either elimination or substitution, because they are certainly far more accurate in the algebraic sense. So here's what we're going to do with substitution. We are going to look at both of our equations here. So we have x minus 2y equals negative 5 and 2x minus 3y equals negative 4. Looking at both of these equations, we want to ask ourselves this. Is one of these two equations already solved for x or y? Meaning, is the x or y all by itself in one of these two equations from the beginning? Clearly, the answer is no, right? So then we move on to question 2, or maybe question 1b. All right, since neither of these two equations has one of the variables all by itself, is one of these two equations in a position to get either the x or the y all by itself more easily than the other? And in this case, the answer is yes. If we take a look here at the first equation, we can isolate, meaning we can get this x all by itself through one little itsy-bitsy algebraic step. And that would be, of course, to take this negative 2y and add it to both sides. We want to move that negative 2y to the other side. All right, so that's what we're going to do first. If we wanted to get this x all by itself, or we wanted to get this y all by itself, that would take a little bit more algebra. You could certainly do it if you want to, but we're trying to take the path of least resistance here. So starting with, again, x minus 2y equals negative 5. To get this x all by itself, one algebraic step. If we add 2y to both sides, what we now, let me switch back to blue. What we'll now have, of course, is x on the left is equal to 2y minus 5. Now, the reason we want to isolate one of the variables, either x or y, from either equation 1 or 2 is because now that we've isolated the x from equation 1, the x is equal to 2y minus 5. We are going to take this value, this expression, 2y minus 5, and we are going to substitute that value into equation 2 wherever we see an x. All right, so what we're going to do is we're going to take this value of x, 2y minus 5, and we're going to substitute that into the second equation wherever we see an x. All right, so again, x, the variable x, is equal to the expression 2y minus 5 that came from the first equation. So we substitute that value for x, right? We now know that x is equal to 2y minus 5. We make that substitution. So let's come over here. 2x minus 3y equals negative 4. So we have 2 times x. And again, x is equal to this expression, 2y minus 5 minus 3y is equal to negative 4. So again, this 2y minus 5 came from the first equation. And now what we do is we're going to algebraically clean up and solve for y. So we're going to distribute 2 times 2y, of course, is 4y. 2 times negative 5 is minus 10. Please do not distribute the 2 to the negative 3y, right? Only to what's inside that quantity. So that minus 3y comes on down, is equal to negative 4. We will combine like terms on the left, so 4y minus 3y is 1y, or in other words, just y. Minus 10 is equal to 4. And then, of course, to get the y all by itself, let's add 10 to both sides. And so what we now have is y is equal to, and 4 plus 10 is 14. So we just solved for y. We now know what the actual numerical value of y is. It's 14, positive 14. So now the question is, well, how do we solve for x, right? Because ultimately what we're hoping for is to find an ordered pair, an x comma y, the solution to this system. So we just found the y, right? So maybe if we go up here, we're looking for an x comma y to be our solution, hopefully. And what we just found is the y component. Now we need to, of course, find the corresponding x. And to do that, we could either back substitute into one of the two original equations that we started with, perfectly fine, or you could make your life a lot easier and take this value of y, now that we know what the actual numerical value of y is, and we can substitute, back substitute, into this equation where we originally solved for x. And if we do that, as soon as we plug in the value of y, multiply it by 2 and subtract 5, we will then have our x value. Or in other words, we'll have x is equal to 2 times y, but we now know y is equal to 14, so we'll pop that in. I'm going to highlight that just so we know where it came from, minus 5. So we have x is equal to, and again, cleaning this up, 2 times 14 is 28, and 28 minus 5 is 23, and so we now have the actual numerical value of x. So we now have the complete ordered pair solution. In this case, 23 comma 14 is our solution. If we were to graph both of these equations on an xy grid, we would see that the ordered pair where those two lines intersect each other is the ordered pair 23 comma 14. Now, of course, you don't have to graph to verify. You could take 23 and 14, substitute it into the first equation for x and y, make sure you get a true statement, and then take your proposed solution here, 23, 14, plug it into the second equation, and also make sure you get a true statement. And if you do, then you know without a shadow of a doubt that your solution is correct. Now, for time purposes here, I'm not going to do that, but I will leave the algebraic check to you. But this is the method by which we would solve a system through substitution, right? Here's one scenario where you ultimately end up with an ordered pair solution. The next two videos that we're going to look at are the scenarios where what happens if there is no solution, and what happens if there are infinitely many solutions. What does the algebra end up looking like? So we're going to take a look at those two examples coming up. But for question 32, we were able to find our solution.